this set of notes, we're going to continue our discussion of estimation. Last time we looked at what was known as the likelihood, and so in this set of notes we're going to talk about what is known as the method of maximum likelihood. So ideally we'd like to find some estimators that are what we call minimum variance unbiased estimators, or MVUE. In other words, it's the smallest, this estimator is going to have the smallest variance among all other unbiased estimators. And the method of maximum likelihood will often result in MVUEs. So let's look at an example. A box contains 4 balls, all of which are either white or red. And suppose that we select 2 balls without replacement and exactly one of the balls is red. So in other words, we're going to say that y is equal to 1. So we want to estimate R, the number of red balls in the box, based off of what we found. So notice right off from the bat we know the following. We know that R, and here we're going to let R be equal to the number of red balls, has to be equal to 1, 2, or 3. And the reason for this is we know that there are exactly 4 balls in the box, and on that first draw we had that exactly one of the balls was red. So we know it's impossible for 0 balls to be red. We also know that it's impossible for all 4 balls to be red, because if we draw 2 balls and exactly one of them is red, that means that the other one had to be white. So R is either equal to 1, 2, or 3. And again, this is because there was 1 red ball and 1 white in the sample. Alright, so notice what we could do is we could look at those 3 possibilities, R equals 1, 2, or 3, and see what is the probability that when we select 2 balls, we get 1 white and 1 red. So if R is equal to 1, then we have the following. The probability that Y would be equal to 1, where Y is equal to the number of red balls out of a draw of 2, is going to be equal to the following. From our red balls, there's only 1, and we chose the 1. From the 3 possible white balls, there were 3, and we drew 1. And then in the denominator, we look at the possible combination of 4 balls, the orders that we could draw 2, and this is equal to 3/6. And then we can do the same thing for if there were 2 red balls and if there were 3 red balls. Using the exact same method, if R is equal to 2, you would find that you get 4 out of 6. And if R is equal to 3, you would find that you get 3/6. So notice that if we look at the comparison of these 3 probabilities, we find that the highest probability occurs when R is equal to 2. So since we observe Y is equal to 1 is more likely when R is equal to 2, we estimate R hat, so notice here R is a parameter, so R hat is the estimate, is equal to 2. So the big idea here is we choose a value of the parameter or an estimate of the parameter which is most consistent with the data that we observe. And really, if we think about this, makes sense, because the only information we're going to have to estimate that parameter is probably going to be the data that we observe from our sample. So what we do is we use that data from our sample, and then we choose the value of the parameter that's most consistent with that data. So we're going to recall just the definition of the likelihood function. So right here, this is copy and pasted from the Module 8 notes, so you've already seen these definitions before. And so then that brings us to the definition of the maximum likelihood estimates, or the MLes. So the method of maximum likelihood estimates, and so notice here we're not restricted to just estimating one parameter. A lot of the examples we're going to look at will just involve one parameter just to make things easy, but we could estimate up to k parameters. And what we do is we choose the values of theta hat 1 through theta hat k, which maximize that likelihood. In other words, what values of the parameters are most consistent with the data that we observe. Because notice when we look at the likelihood, what we have here is the likelihood looks at the parameter conditioned on the observations. So suppose that y1 through yn are discrete random variables. Then just as a reminder, the likelihood is equal to the probability. So maximizing the likelihood function is the same thing as maximizing the probability of obtaining the data we observed, which is what we did in that previous example. So it's often easier to work with the log likelihood, and so you'll notice here that the log likelihood function is often denoted with a lowercase l, whereas the likelihood function is denoted with an uppercase L. So assuming that the log likelihood is differentiable and bounded above in theta, the maximum likelihood can be found by differentiating with respect to theta and setting equal to 0 and solving. So in other words, here's what we would solve for 0. Now theta here, I have a single theta, but if you remember we had theta 1 through theta k up above, you can think of that theta with no subscript as being a vector that is comprised of k thetas. This is also known as the score function. So if you ever see anything that refers to the score function, what it's really talking about is differentiating the log likelihood with respect to theta. Now, one thing to note here, and this is a common thing that happens, we're going to differentiate this with respect to theta to find the maximum. But remember, to ensure that that really is, you always want to take the second derivative just to double check that. All right, and so we have some large sample properties here. For a large n, under certain regularity conditions, the MLE will be approximately normally distributed. So this is another place where the normal distribution comes in and helps us out. All right, and remember here's that information function that was back from when we looked at the Kramper-Rao inequality. All right, so let's look at an example here. We're going to let y1 through yn by IID binomial distributed 1p, and we're going to observe y1 through yn, and our goal here is we want to find the MLE of p. All right, so we had already looked at the likelihood, so let's write out what that likelihood is. So we have L of p is equal to L of y1 through yn given p, which is equal to p, the sum I equals 1 to n yi, 1 minus p times n minus the sum I equals 1 to n yi. And so notice, if we let y be equal to the sum of I equals 1 to n yi, then we have the following. P to the y, 1 minus p to the n minus y. So our goal here is we need to find the value of p which maximizes the likelihood. So one option would be is we could take the derivative of the likelihood and set it equal to 0, but it ends up that this can be fairly difficult. So instead, what we do is we consider the function the natural log. And so by looking at the log likelihood is going to be strictly increasing. So maximizing the likelihood is equivalent to maximizing the log likelihood. So this is why we generally work with the log likelihood instead of the log likelihood. So here, I'm going to use a lowercase l, so this is going to be the log likelihood of p, and that's going to be equal to the following. All right, so now we've got our log likelihood function. So one of the things that using the log likelihood does for us is it turns the product that we previously had into a sum. And so by doing that, the sum is much easier to differentiate than the product is. So again, working with the log likelihood is almost always easier. All right, so let's take that derivative with respect to p. So I'm going to take the derivative of the log likelihood with respect to p. I'm going to get the following. And remember, this is that score function, so what I'm going to do is I'm going to set this equal to 0. Now, as soon as I set it equal to 0, notice what I'm doing is I'm taking that derivative, I'm setting it equal to a fixed value. So when I do this, I actually no longer have p. At this point, that's when I'm setting, okay, this is going to be my estimator. So as soon as we set it equal to p, what we do is we change our p's over to p hats. Okay, so notice once I set it equal to 0, that's when I put the hats on everything. So this suggests the following. Oh, sorry, I had a -1 there. I knew I was forgetting something. So now we have this. So notice that this suggests the following. Which then suggests so notice here we have that the yp hats cancel there. So here we have the y equals p hat n, or in other words, we get that our estimate is equal to y over n, which is exactly what we've seen before for the MLE. So therefore, the MLE is p hat, which is equal to y over n. And it ends up that you can show that this is the MVUE. And then just remember, whenever you're showing that anything is a maximum using derivatives, you do want to then follow up with the second derivative test. And what we want to do is we want to take that second derivative just to show that this is a maximum. So in other words, we want to show that it's always negative. So on your homework, I'm not going to do it here because I'm out of space, but do go ahead once you found that first derivative. So in other words, we're looking at here. Go ahead, do find the second derivative as well and show that it is negative to show that this actually is a maximum and not a minimum. All right. So let's look at another example. So suppose that y1 through yn are IID, and here this is what's known as the logistic distribution, or it's often denoted as logistic theta. And so here we're going to find the MLE, and we're going to notice that this one is a little bit different than the last case that we just looked at. So the very first thing we're going to want to do is we are going to find that log likelihood. And so here, if you go through and find the log likelihood, it's going to simplify to the following. So notice here, all I'm doing is I'm taking the log of that distribution. And the reason that we've got the xi's where we didn't have them up top is, again, remember we've got a sample. Oh, I'll fix this in your notes. These should be x's here. We have a sample from 1 to n. Right, so it can be shown. This would simplify to the following. And so you do want to check this math. So now that we have our log likelihood, the first thing we're going to want to do is take that first derivative. And we are taking this derivative with respect to theta. And then next thing we would want to do is set this equal to 0, and we would want to solve. So in other words, we're going to have n minus 2 sum I equals 1 to n. And remember that once we set this equal to 0, we're now looking at a specific value. So instead of theta, I'm now going to replace that with theta hat. So we can rearrange terms here. Oh, and we're setting that equal to 0, and we would have the following. Now, at this point, normally we would want to solve for theta hat. But notice that this isn't going to simplify nicely. Now, it is possible to show that this has a unique solution. And so we could look at the derivative of the left side of the equation and look what that simplifies to. So and then we could go further to say it's a strictly increasing function of theta. But we can't find an exact solution here. We can only show that the solution is a maximum. So what we're going to look at in the next set of notes is what can we do when this happens? We could show the existence of an MLE here, but we can't actually find what it is in closed form. And it ends up that there are different numeric methods to help us out when this happens. This does happen quite often. And so we're going to look at what is called the EM algorithm and Newton's method to find these maximums. So there are some nice examples which we can look at where we get closed form solutions, but this is an example where we don't. So we're actually going to pick up this example in the next set of notes. Alright, but let's look at another one where we could nicely find what the MLEs are. And this one's an important example because this one is the MLE of mu and sigma squared. So let's look and see what we get for the MLE of mu and sigma squared. Alright, so we're going to start out, we're going to write out what our likelihood function is. And notice this is a case where our likelihood function has two parameters. So remember before we could think of that definition that we have that single theta as being a vector of parameters. So here we would have a vector of two parameters, which are mu and sigma squared. And remember, the reason this doesn't look like the PDFs that we've seen before for the normal is because remember that we have a sample from y equals 1 to n, so you're really multiplying that PDF n times for each of them since we do have that independence. Okay. So there's our likelihood, but remember, we're not going to work with the likelihood, we're going to work with the log likelihood. So I'm going to write out the log likelihood next. And for our log likelihood, we're going to have the following. So this gives us the following. Alright, so now that we have our log likelihood, we can go through and find the estimators for mu and sigma squared. So for each of these, what we're going to do, for mu, we'll take the first derivative with respect to mu, and for sigma squared, we'll take the first derivative with respect to sigma squared. So we're going to find mu hat first. Right. So to do this, I'm going to take the first derivative of the log likelihood with respect to mu. And then remember, as before, we're going to set equal to 0. Remember, once we set equal to 0, we're looking at a specific value. So instead of mu, I'm now going to write this in terms of mu hat. And then also, once we set it equal to 0, we're really looking at a specific value of sigma as well. So I'm going to put sigma hat squared there. And then I'm going to simplify this to get mu hat by itself. So notice that the MLE for mu, or mu hat, is equal to the sum I equals 1 to n yi divided by n, which is y bar. So this should be no big surprise. We use the sample mean to estimate the population mean all the time. We've seen that it's got other nice properties. So it ends up that the sample mean is also the maximum likelihood estimate of the population mean. Alright, so next, we're going to find the MLE of sigma squared. So the first thing we're going to do is write down again what our log likelihood was. Now, we want to find the MLE of sigma squared. So we're going to want to take the derivative with respect to sigma squared. And notice this is going to be kind of hard because here we've got a sigma and here we've got a sigma squared. So all I'm going to do to fix that is the following. So let me rewrite what I had here where that got erased. Notice that what I could do is if I divide by 2 here and I square the sigma, that is the exact same term by the rules of logarithms. So I'm going to do that. And then the other thing I'm going to do, just to make this easy on myself, is I'm just going to let theta be equal to sigma squared, because I'm looking for the estimate of sigma squared, so it really is its own thing. So now let's rewrite this. So we've got the natural log with mu and theta. So here we're going to have negative n over 2 natural log of theta minus the natural log of the square root of 2 pi minus 1 over 2 theta times the sum I equals 1 to n yi minus mu squared. Alright, so now my next thing is I'm going to take the derivative. And this time I'm going to take it with respect to theta. And just like before, we're now going to set this equal to 0. So when I do this, I'm going to have the following. And then what we could do is, since this estimate does contain the parameter mu, is we could replace mu with its MLE, which is y bar, and we're going to replace theta hat with sigma squared hat. Again, that's just a notational thing. So notice we get that sigma squared hat is equal to the sum I equals 1 to n yi minus y bar squared divided by n. But notice that is not the estimator that we use. The estimator that we typically use has n minus 1. And we've shown that if we have n in the denominator, that's not actually an unbiased estimator, that's a biased estimate. So it ends up that y bar and sigma squared hat are the MLEs of mu and sigma squared if the data are normally distributed. So notice there are options for different estimators, but this particular estimator for sigma squared hat is not unbiased. So the MLEs are not always going to be unbiased. So that's going to conclude our notes on MLEs for now. We're going to focus in the next set of notes and in labs how to find those MLEs using numeric methods.